So we've learned about radioactivity. So radioactivity is the rate basically of your nuclear reaction, and it's expressed in terms of disintegrations per second. We've learned about the equations that we can use to determine the radioactivity or the amount of your radio atoms in a sample at a specific point in time. We've learned about your decay constant, how to calculate mass of a radioactive sample and specific activity. And we also saw that nuclear reactions, their rates are exponential in nature. Now we talk about another quantity we call half-life. So it's not the game, the computer game Half-Life. If there are some of you here who are familiar with uh, the online computer game Half-Life, it's a very old game. I don't think they still have it now. I'm not sure. So half-life, from the name itself, this is half of the life of your radioactive sample. So technically, this is defined as the time interval for a given number of nuclei to decay to one half of the original value. Okay, or we can also define this as the time interval for the radioactivity to decrease by half from its initial value. And practicality wise, it is actually more convenient to compute first for the half-life before you find the decay constant. So a while ago, we saw how to use the equations to determine the decay constant. But in terms of practicality, half-life, I think it's better if you compute first for the half-life and then determine the decay constant from the half-life, whichever is more convenient based on the method that you used. Okay, so again, this is defined as the point in time. So this is time t, t1 half, wherein your n sub t is equal to half of your initial amount. Or it can also be defined as your radioactivity is half of the initial radioactivity. Okay? So remember, we had this equation in the previous video, right? Now, since n sub t is defined as the initial divided by 2, so we have n sub 0 over 2 equals n sub 0 times exponential raised to negative lambda times t1 half. Because this one is only possible if we are at that half-life, at that specific point in time, which is the half-life. Okay, so we can cancel out n sub o or n sub 0 here. And now we have 1 half equals exponential raised to negative lambda times t or half-life, t1 half. Now we need to isolate t1 half in this equation. So what we do is we get the natural logarithm of the two sides of the equation. So we have ln 1 half or ln 0.5 equals negative lambda times t 1 half or half-life. Yep. And finally, we have t1 half equals ln 0.5 over negative lambda. Now, ln of 1 half or 0.5 is equal to negative 0.693 approximately. So we have negative 0.693 over negative lambda. So we can cancel out the negative sign there. And we now have an equation for half-life, which is t1 half equals 0.693 over lambda. So this is our equation relating the decay constant and the half-life. So here is a sample problem that we can work on and apply the equation or equations that we so far are learning in this module. So we have a radioactive sample of metastable technetium-99 containing 370 megabecquerels or 10 millicuries of radioactivity at 9 a.m. So it was measured at 9 a.m. and this is the activity. What will be the radioactivity of this sample at 3 p.m. on the same day? The half-life of metastable technetium-99 is 6 hours. So, how much time elapsed from 9 a.m. to 3 p.m.? It's 6 hours, right? And we are given the half-life of metastable technetium-99, which is also 6 hours. So what does this mean? It means that at 3 p.m., it means one cycle of half-life happened in this sample of metastable technetium-99, which means that the radioactivity of this sample must be half of the starting activity at 9 a.m. So we can, even without performing any computations, we can tell that the radioactivity at 3 p.m. is half of 370 megabecquerels or 185 megabecquerels or 5 millicurie. Okay, how about if we use the equation? Okay, so we have, okay, how do we use this in terms of your radioactivity? So in terms of your radioactivity, your equation will be, so R sub T equals R sub 0 times 1 half raised to T over your half-life. So at any given time, divide it by your, time interval. At any given time interval t, divide it by your half-life. This will be the exponent of your 1 half, and multiply this by your initial radioactivity. So for this example, we have RT equals 370 megabecquerels times 1 half raised to 6 over 6. So this will give you 185 megabecquerel or 5 millicurie, which is half of the starting radioactivity. Okay, what if we measured the radioactivity 6 p.m. on the same day? So that would mean 9 hours passed, right? From the initial measurement at 9 a.m. So if it is 9 hours, then following our formula, that's R sub T equals R sub 0, which is 370 megabecquerels times 1 half raised to 9 over 6. So this one will give us a value of 130.81 megabecquerels. Okay, so this is how we solve for the radioactivity, or if we are talking about the amount N sub T of our radioactive sample, these are the equations that you need to use to solve for the remaining amount or the remaining radioactivity in your sample. Okay, another example. So again, it's metastable technetium-99. It was calibrated at 7 a.m. and contained 555 megabecquerels per ml or 15 millicuries per ml of radioactivity at that time. If the prescribed dosage to the patient is 555 megabecquerels or 15 millicuries, determine the volume of the preparation that will have to be injected at 10 a.m. So, if we just analyze the problem first, at 7 a.m., we already have the required dosage, which is 555 megabecquerels per ml, but it needs to be administered at 10 a.m. So, this means that we need to administer more than 1 ml of this metastable technetium-99 sample, right? Because as time passes by, this radioactivity measured at 7 a.m. decreases. So how do we compute for that volume? So again, we have R sub D at 10 a.m. We need to measure the radioactivity at 10 a.m. So let me just write 10 a.m. as a subscript here, equal to 555, which is the initial measured at 7 a.m., times 1/2 raised to time elapsed is 3 hours divided by 6. So the radioactivity at 10 a.m. is now equal to, that's 555 times zero point 0.5 raised to zero point 0.5. We get 392.44 megabecquerels. This is at 10 a.m. But at 10 a.m., what we want is 555 megabecquerels. So the volume that we need, okay, this is actually per ml, right? The unit of 555 here is megabecquerels per ml. So what is the volume that we need? We need 555 megabecquerels of radioactivity at 10 a.m. And at 10 a.m., our sample has an activity of 394 megabecquerels per ml. So dividing 555, that will give us 1.41 ml. So you need to give 1.41 ml of this metastable technetium 99 sample so that at 10 a.m., the patient has 555 megabecquerels of activity from this technetium 99 sample. Okay. Now, we also have another quantity called average half-life. Average life or TAV. So this one is related to the half-life of the radionuclide or even the decay constant as given by this equation. So it's 1.44 times the half-life or equal to simply the inverse of your decay constant. So why do we have this average life? In radioactive decay, not all of your radioatoms decay at the same time. So each individual radioatom exists for a different period of time. So average life gives us the mean or the average of all of these intervals for which your individual radioatoms remain in existence. So it's because it is possible that in a certain sample, you have one radioatom that underwent the nuclear reaction earlier than this. It means that their starting points are quite different or different, actually different. So their existence are also different. I mean, the intervals for which the individual radioatoms remain in existence are different. So we can also quantify this in terms of the average life. Next, we also have what we call the biologic half-life. So the biologic half-life is expressed in this using this equation, which is similar to our decay uh, law of decay. So we saw the equation n sub t equals n sub 0 times e raised to negative lambda times t. But if we are considering this in the biological context, then there are other factors that can affect the disintegration of a certain radionuclide. And to take this into account, we can measure the decay constant in a biological system. So we have here a lambda sub bio, which is again the decay constant in a biological system. And in fact, this is also in consideration of the organ in which your radionuclide will undergo the nuclear processes. So they can have different half-lives in the thyroid, in the liver, in the lungs. And we also need to take into account the metabolic processes that can take place, like excretion or simple diffusion or other biomechanisms. So the amount and m sub t of a biochemical or a drug present in the biological system at a certain time t can be determined by this equation, provided that we have the original amount, the m sub 0, and the decay constant in the biological system. So again, this decay constant in the biological system is also related to the half-life or the biological half-life in an equation that is the same as the one that we derived earlier. So just to distinguish this from your physical half-life, so we include here, okay, bio. So this is in the biological context or system. Now, sometimes the disappearance of a drug or a chemical in the biological system cannot be simply described by this equation. So sometimes it can actually be described in terms of a series of exponential terms, like what you can see here. It means that you have a very complicated behavior for the disappearance of this radioactive biochemical drug or compound. So, yeah, sometimes you can have this very complicated equation to describe the disintegration of your radionuclide inside a biological system. So each constants here, the A1, the A2, these are like proportionality constants, and your decay constants, lambda 1 bio, lambda 2 bio, etc., are also determined experimentally for a given drug. And lastly, we have the effective half-life. So the effective half-life is one wherein you consider the biological half-life of a certain radionuclide. So when you deliver radioactive substances or drugs in biological systems, of course, you have to consider, aside from their physical decay, their biological elimination. So you see here the effective decay constant, the lambda effective, which is simply the sum of the physical decay constant or lambda and the biological decay constant lambda bio. And if we substitute each of these lambda terms by their expressions containing the half-lives, so we have this 0.693 over the physical half-life plus 0.693 over the biological half-life equals 0.693 over the effective half-life. So if you know the physical half-life and the biological half-life of a radioactive substance or drug, then you can compute for the effective half-life of that radiopharmaceutical. Now, this is under the assumption that in your biologic half-life, this one, we are assuming a mono-exponential behavior. So it doesn't follow this series of exponential terms, but rather only a mono-exponential behavior. So of course, if it's the series of exponential terms, then we have a lot of terms in this equation. So for the purpose of this subject, we will only consider mono-exponential biologic distribution and disappearance. So always remember that your effective half-life will always be less than or equal to the shorter of these two terms, the physical half-life and the biologic half-life. So it can only be equal to which, so if you have the physical half-life as lower in value than your biological half-life, then your effective half-life can be equal to your physical half-life or can be less than your physical half-life but never greater. Okay, let's try solving an example, and that is the end. So we will solve this And that will be the end of this video series on nuclear chemistry. Now, before we go to this, for additional reading, you can read additional chapters on the ebook that I sent you, which is in EPUB format. So all of the contents here came from that book. So all of the examples I showed you are solved examples in that book. So please try practicing. Please try to practice solving the problems at the end of the chapters. So I used chapters 2 to 5, I think, if I'm not mistaken. Chapters 2 to 5 from that book. In other chapters, you will see more specific radionuclides used in specific contexts in nuclear medicine. Okay, so let's go into this problem. We have xenon 133, which is a radioactive inert gas. This is used for lung function studies, and its physical half-life is 5.3 days. Its biologic half-life in the lungs is about 0.35 minutes. Determine the effective half-life of xenon 133 in the lungs. This is again a straightforward problem. So you have the formula, which is 1 over the effective half-life equals 1 over the physical half-life plus 1 over the biological half-life. So you might notice all the numerators are now 1. That's because we can cancel out the 0.693 from our previous equation. So plugging in our values, but first you have to note that the units are not consistent. So this one is in days, this one is in minutes. So you have to keep the units consistent with each other. So we can use minutes, I think. Yeah. So if we plug in the values, so we have 1 over the effective half-life equals 1 over 7,632 minutes. So that is the conversion of 5.3 days plus 1 over 0.35 minutes. And you will find that the effective half-life is 0.35 minutes. Okay, so one observation that can be made about your effective half-life, your physical half-life, and your biological half-life is that whenever one of the half-lives, either the physical or the biological half-life, is very large in comparison with the other, 10 times or more, then the effective half-life is most likely would your effective half-life would most likely be equal to the other half-life. Okay, so this means that if you have your physical half-life much greater than your biological half-life, okay, then your effective half-life will be close, if not equal, to the biological half-life. Or if your biological half-life is much greater than your physical half-life, then your effective half-life will be close or equal to your physical half-life. Okay? And that's it for the lesson, nuclear chemistry. See you all next time.